Can you hear me?
Yeah.
Okay. Third step. So first it's saying PTR equals null. Okay. New node equals PTR. Okay. PTR equals PTR next. PTR next. Okay. Why is it there? Because so here is where they're initializing, right? So PTR is holding the value of that initialization, isn't it?
Yes, but there is set new node to PTR. So
This is
I
incorrect.
think
How is it there in the book? Let's check that. What is that? Singly linked list? Okay, let's see if we have linked list implementation. Algorithm begin if the list is empty. Then inside, see, they are not even writing all of that. If the list is empty or a create or a new element comes before the start, then insert a new element as start element. Else, if the new element comes after the last element, insert the new element at the end of the element. This is the one, right? Or is it different?
yes, I think this is the only algorithm they have. The linked list in the book is it's implemented in a very confusing way.
The book. Yeah.
Yeah.
Let's stick to this. Maybe we'll try to understand what's going on here.
I think the step 3 is unnecessary. If we remove that, it will still be correct.
Okay, fine. I don't mind removing it. Let's consider it's not there. So initially PTR equals null, and then we set new node equals PTR. Okay, which is the whole thing. The whole node equals PTR. Then new node data. We set the data value to the value, and the next, which is this guy, to the head, because head would already contain the old link. That's what we want. Then set the head to the new node. So after new node has got this value, then we go ahead and assign the head to this guy over here. So head to new node. Do you think this setting head to new node is correct, or should it be new node next? No,
Uh,
not next. It should be. No, it's correct. I think
it's correct, yeah.
correct. Data new node is the head. Okay, fine. So let's try to practice this, because practicing is also important. We can't just take a look at it and think that we've done it. So let's try to remember. So step one, what do we have to do first? PTR equals null. Step two, uh, let's see, new node. Why is this required? Write overflow. Go to step seven. End of if.
I think if the allocation failed, then you write overflow.
Okay. So new node will be equal to PTR. Step three, new node.
Step 1 is if PTR equals null.
Okay. And write overflow, right?
Yeah.
So if that condition is met, then that means there is error. Right, overflow and go to step 6 because we skipped the step 3. The new node data was value, new node next equals head, new node no head actually, head equals new node head 7 exit. So set, let's see what we missed. So if ptr equals null, write overflow and go to step 7. Of course we have to do end if also. And if once I'm done, I'd like one of you to try, so pay attention. So set the new node to ptr. So let me go step by step. So initially we check if the ptr is null, pointer is null. So if pointer is null, we write overflow and just exit. If that's not the case, we set the new node equals ptr, which means new node is this. Currently it's empty, doesn't have anything, but of course it has the two columns where one contains the value and one contains the pointer address to the next one. So it doesn't have anything right now. It's empty. It doesn't have the pointer address, it doesn't have the value. Just new node. So we set the new node equals ptr. Then you set new node data. So the left part, the data part, we set equals to value, whatever you want to set. Then new node next, which means this guy, we want to point it to the this guy, but head has that information. Head is already pointing to that. So if we can grab this information from the head, we can set it equal to this one. So that's why we're saying the next of the new node, the next column, grab it from the head. So that's why we're saying head equals this. Then we're setting the head. So now because we grab that address of this guy, now we have to set the head to this one because we are inserting this element. So first element becomes this instead of that. So that's why the head has that value. So we're saying set head to the new node, which is now the head will point to this one. Earlier it was pointing here, and then exit. Are we missing any steps, Maya?
It looks correct.
Okay, Kritika, you want to try? It's you can take a reference from the book if you want. Not the book, but the slide.
Yes, no, I think I understood when you explained it.
So
I'll
you want to
try.
try? Okay,
Yes.
so share your screen and try. Because we
Uh,
have to try also. Otherwise, by looking at it, we can't establish that we know it.
okay. I'll write on Google Docs.
Yeah, that's fine. That's
That will be
fine.
right.
Share your screen and write.
Yes. Okay. Share screen. Share screen. This one. Okay.
See, we are
Okay.
going to be relaxed only for a couple of days, but I'm telling you, just the day before exam, we'll start panicking. We won't really have the time. So, क्या पढ़ लें?
हाँ मेरे साथ एग्जाम के एक दिन पहले होता है and although that didn't happen for DBMS but yes I panic.
Hmm.
The first is start.
Yeah.
Okay, then there is new node,
Then we have to check if the pointer equals null.
right? If the um pointer
Equals.
equals null, then go to step 7.
Should we also have a step like allocate pointer
Mm,
PTR? Because it's not clear what pointer is from the second step.
Yeah, why
mm,
not?
mm, mm.
Maybe what
Uh,
you can do is, Samaya, on that sheet now, cut the below part and write it and paste it.
Okay.
Yeah.
And I think we should have the algorithms for inserting at the in the middle and the end also, because it's a 10-mark question.
Oh my God. Yeah, we have to. For now, Kritika, just go on with what we have.
Okay.
So yes, if
Then the
this is,
pointer
yeah, correct.
is divided in two, which is no, not the pointer. That's the node. New
Then we are
node.
setting the new node equals pointer.
New node equals pointer. Okay.
I remove the is divided into and use set SCT before new node, new underscore node on line, yeah, 4. New
And,
underscore node. It's one word underscore.
yes.
Yeah.
New node. This goes to the pointer, and then the other part of the node should go to the head.
So
It
there
should.
are two. Okay. So understand what we've done now. So first we first check the pointer is null or not. Then we have the new node. So currently new node has two things. Okay. On step 4 we set it to the pointer, which is fine. But now we have to set two things. We have to set its data, which is the left column, and then we have to set the pointer also, which is in the next. So again we'll say set new node
New node.
arrow.
Arrow.
Arrow will be like close, like no space between new node and arrow.
Okay.
And then data equals value.
Capital.
Similarly, we have to, this is fine. Similarly, we have to set the next to new node next to head. Use set.
Arrowhead.
Yeah.
Arrowhead.
First you have to set the next, next next. Yeah, arrow is fine. You have to use arrow.
Okay, I'm a little bad at code.
Don't worry, it's completely fine. You're doing well. Equals head. HEAD. So you see, do you understand what's happening here? So at line, so basically new node has two columns, right? The left part needs data and the right
And
part needs
needs
pointer,
the yes.
right? To the next element. Currently head already has that information. That's why we're setting the next of the new node to the head, because head has that information of the next node. Got it?
And,
Now
mm,
in the next step,
the head has both data and pointer, or just the
no,
data?
had just had the value of the next node. That's why
Each
we set
node
the
has each node has data and next.
yes. But she's asking about the head. Does head has both? So Kritika, look at that diagram. You'll see. You understand.
We are putting new node before head, so new node next points to head.
Hmm.
Okay. Okay,
So
got it.
last step is to set the head to the new node. I know it's confusing, but it's very confusing if you ask me. But it's okay.
No,
You're doing
I
well.
think you guys made it clear. I'll summarize. Okay. So
Hmm.
we start and then we allocate the pointer because
Yeah.
that's we're starting, and then
Hmm.
initially that part is null.
We
The
know we're
point.
checking if it's null or not. If it's null, then we don't want to go ahead. We want to
Okay.
send the user to the step 7 and exit because we just
Oh,
initialize the pointer, right? So it should not
hmm.
be null.
Yes, it should have something. and then we
Yeah.
check if there is an and then so the pointer, we know if it is not null, then it has a node, it has a new node, and then the new node has two parts. One part is the pointer, one part is the data. So
Mm-hmm.
now for the data, uh, we set the pointer, and then the data needs to have some value, and that
Mm-hmm.
value is already given in head. So from head, that value is taken,
Okay, okay.
and
A little rewind here. So at point, so you were right in saying that the node needs data and needs the next, which is the pointer to the next data. Okay. So at line 5, you see you're setting the data
hmm,
to a value. Now you're setting, then on line 6, you're setting the next to the head. Can you open the, uh, what do you call it, the slides?
yes, I'll have to. I actually shared a tab. I'll share the full screen. Share, share screen, share screen, entire screen share. Okay. Um. Okay.
Yeah, that
Yeah.
one. Just make it big, slideshow. And click on that slideshow
Sorry. Um.
on the top right corner.
Yes. 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 I'm going. Yes.
Okay. So look at that. So look at the new node on the right in the
Hmm.
diagram. The new node. So initially this doesn't exist, right? So if it doesn't exist, you see on the
Then the
right there is another node,
hmm.
uh, the green and orange.
Yes.
This one. So this is the original position. This is the condition of the stack initially. But now we want to insert another node. So each node has two pieces. One is the data, and second is the pointer to the next one. So that's what we want to do. We want to insert it. So earlier, the head will be pointing to the old node. So can you see there's old link coming from
Yes.
head? So it's pointing to the old one, correct? So it has the address of the next node. The head has the address. So what we want to do is we want to, when we create new node which you created, we have to set two things. We have to set the data and we have to set the next pointer. So that's what we were doing. In the data, we were putting value at step 6 which you wrote, and the green box that you see,
Hmm.
we are setting that to the next node. But how are we setting? Head has that information already, the dotted one. So we're pulling that information from the head. Okay, that's why we are setting the next to the head.
And if we want to add one more node, do we add
Same,
it here and
just
then
go to step 1 and repeat till step 7
add
steps.
and take it from head? So how does okay, understood,
So
understood.
head needs to point to the very first node. Okay.
Hmm.
So first we grab, then we tell him, okay, so what do you have the information about the next node? He said, yes, I have it. I have the old one. You want to take it? So it gives that information to the new node. Once new node has that information, it tells, okay, so now you've given me that information. Now you point to me because I'm the new guy. Okay, don't point to the old one. So that's why the old link gets dotted, because it stops pointing to the old one. Now it starts pointing to the new node. So now the new node becomes the first node. Do you understand?
Right. Yes. Yes. Okay.
That's what we're doing in your steps. So go back to your code. Your
Hmm.
Yeah. See that step 5. What are you doing? You're setting the data to value and you're setting the next to head, because head has that information on the
Value.
step 6.
Yes.
Your new node is saying, you know what, give me that value. Whoever you're pointing to, I don't want you to point to that person now. Point it to me. So give me that value first. So I get that value. And then on step 7, so create a step 7,
Um. Yes.
set head equals new node. So new node said that give me that value first, whoever you were pointing to, give me that value. Now that you've given me the value on step 7, now point to me because I'm the new guy. Understood?
Yes. Yes.
That's it,
Okay.
exit. So Maya, if you find any other solution to this which is better, then just replace that with that, because if it's 10 marks then we should really be writing it properly. I'm not saying this is not good enough, but we can of course explain and make it more detailed. But
Yeah.
yeah, it'll be good if we have something better. But try to not change too much in this, because we build a concept and then you have to forget it and create a new one. Just improvise that if possible.
Okay.
Cool. Let's move on to the next one, which is the tree. I'm going to share my screen. We'll finish it off at 11:30. Is everyone okay with 11:30? Because we haven't
Yeah.
covered much. Okay.
I'm okay with that.
Sumaya, are
I'll
you
have
okay?
to leave in about 10 minutes because I'm
That's
sleepy.
fine. That's fine. So then I think let's everyone drop in 10 minutes. Do you think can you push till 11:15, Sumaya? Which is 15 minutes?
Yes.
Okay, let's make it 11:15. I'm telling you, I'm also sleepy. The only reason I'm doing this is because I know we don't have time. I feel DSA is not complete. There's a lot to do in DSA,
Yeah.
Yeah.
and it takes so much time to build that concept, because it's not easy. It's not like those warehouse and tree house that you do.
Yeah, you have to understand everything.
Yeah, yeah. There's so much of algorithm here. There's so many steps you have to remember. You spend so much time on one slide so that at least gets in your head. Now, what's the point of just reading if you can't retain that information? Okay, so let me give you my understanding on the tree. Is my screen being shared?
Yes.
Who wants to be my alarm clock and kind of buzz in 15 minutes?
I'll do
I'm
that.
pretty sure I thought Sumaya will say that. She is sleepy. Sumaya is thinking maybe I'll sleep before that, so it's better I don't raise my hand. You never know,
Yeah,
she
I'll
dozes
do
off.
at 11:15.
Sorry?
I'll stop you at 11:15.
Excellent. Okay, so let me
Thanks.
give you a brief idea about. And now she's speaking. Okay, so I'll give you a brief information about tree because I just studied that today in between my work. So yeah, so tree, unlike stack and arrays, which are basically linear data structure, like it goes in a sequence. Here you have a hierarchical structure. It is not linear. It's non-linear. So based on the information I just gave you, you can derive a definition that it is a non-linear data and is non-hierarchical, used for non-hierarchical data. Sorry, for hierarchical data. So let's say you want to denote the hierarchy of a particular company employees. You can do that using tree data structure. You can say that you have a boss, under boss you have the team leader, under team leader you have the mentor, under mentor you have the employee, which is at the base level. So something like that. So a tree is one of the data structures that represents hierarchical data and is non-linear. And some of the key things to remember is that in the tree, you have a root. The first element is the root. Then you have children. So these guys are children. Uh, when children are adjacent to each other, these are called siblings. These are also siblings. And the ones that they don't have children are called leaf nodes. So these guys don't have children, so these are called leaf nodes. So it's defined as a collection of objects or entities as nodes that are linked together to represent or simulate hierarchy. A tree data structure is non-linear data structure because it does not store in sequential manner. It is hierarchical as elements in a tree are arranged in multiple levels. In a tree data structure, the topmost node is the root node. Each node contains some data. Yeah, so each one of them will have some data. And data can be of any type. So I think this is something important we should highlight. Each node contains some data, and data could be of any type. It's not that important that we have to make it bold. Some data can be any type. Okay. Each node contains some data and the link or the reference of other nodes that can be children. They can be called children. Okay. So yeah, I missed that part that these guys are called children. Nodes that do not have children are called leaf nodes. Moving on. How a tree is different from binary trees. This is your general tree. This is a binary tree. As far as the knowledge that I have, uh, in a binary tree, you can only have between 0 to 2 children. You cannot have more than that. Here you can see that you have more like 4 children for one node, but here you only have maximum 2. So this guy has 2 children. This guy has 2 children. Similarly, this guy has 2 children. So let's take a look. So general tree is a tree in which node can have many children or nodes. That's what we established. In binary tree, each node can have at most 2 nodes. General tree, the subtree of a general tree do not hold ordered property, while subtree of a binary tree hold an ordered property. I don't know what that means. Kritika, do you know what that means?
I think by order, I'm not fully sure, but I think it means what we discussed that day, that the left
Following a
part,
sequence.
yes, it's always ordered like the left part will be smaller and the right one will, this part will be equal to zero or great or smaller, and this part would be greater on the right. So while in a generality tree it can be random.
So they're not really following a pattern or an order. This is what it means, right?
Yes, yes.
Okay. In data structure, a general tree cannot be empty, while this can be empty. Okay. Binary tree can be empty. Okay, I don't know what that means. In general tree, a node can have at most n number of child nodes, while a binary tree, a node can have at most 2 number of child nodes. What's the difference between this and that? Tree in which node can have many children nodes and then at most 2 nodes.
It's the same.
Okay, and you have to put LOL after that, right? If I ask you to do a story. Yeah, I don't remember the whole thing you wrote, but I do remember that you put 3 points at the same LOL. Okay. In general tree, a node can have at most n number of child nodes, while binary tree nodes can have at most 2 number of child nodes. In general tree, there is no limitation on the degree of node, while a binary tree, there is a limitation of degree of a node because nodes in a binary tree can't have more than 2 child nodes. So again, we have to understand what this degree of a node is. Maybe tomorrow, not tonight,
And
because
the
otherwise,
fourth and fifth points contradicting. It's
contradicting.
saying a node can have at most n nodes, so that means it can't have unlimited nodes. And then next they're saying there's no limitation on the degree of a node.
A node can have at most n number of child nodes. N number is saying,
Yes,
and
it's
you're
saying
saying
at
fifth.
most, which means that there is a limit.
Hmm. Yeah. No, this is talking about degree. This is talking about number. The difference in degree and number.
Yeah, that's what degree is. Degree is how many children a node can have.
Okay. Okay. You'll probably have to kind of omit one of these and look for a better pointer for that then. While in binary tree, there's a limitation on degree of the node because nodes in binary tree can't have more than 2 child nodes. Okay. In general tree, there's either zero subtree or many subtree. Uh, okay. You know what a subtree is, right? Tree within a tree. So this can have either zero or many. This there are mainly 2 subtrees: left subtree, right subtree. Again, Sumaya, please look at this. We don't want to be learning something incorrect. Please look at it when you have time tomorrow, uh,
Okay.
and see. If something is wrong, let's remove it. Just add yours. We haven't spent too much
Yeah,
time
I'll
on
check.
this. Please do a proofreading, make corrections as necessary. was laughing so much when somebody behind me in the examination asked me, "Hey, tell me what is data mining?" Go to Bangalore and find out. You might get an answer. Okay. Two types of traversal of binary trees. Pre-order traversal. Each node is visited before its children are visited. Okay, this is what you wrote, right, Kritika? And you can explain this part also, correct or not?
Uh, mm, this is from the book, so I think it's right. But no, no, I'm not fully sure. I can't explain it.
That's fine. Do
I
the
added
topics
a simpler example on the next slide.
for the same.
Yes, for the tree traversals. Because I found these trees a little confusing.
That's fine. Let's go through them. So types of traversal. So in examination paper, they've only asked for two, but I know there are three. So in blue slides, I've put two and put the third one like kind of throwed it outside uh, in one of the slides. So each node is visited before its children are visited in the pre-order traversal. So traversal means like I think going from one node to another, right? When maybe for searching purposes or any other purposes, that's traversing within the tree. So pre-order traversal means each node is visited before its children are visited, which means you'll go like that. You will visit that node, then you'll go to its children. The root is visited first. You'll start from top, I guess, and you go like that in the downward direction. Algorithm. Visit the root node, traverse the left subtree in pre-order. Pre-order is the same, going from the top and going to the bottom. So go to the left part of the subtree in the pre-order. Traverse the right subtree in pre-order, which means first traverse this guy, then traverse the right. As each node is traversed only once, the time complexity of pre-order traversal is Tn equals On, where the n is the number of nodes in the tree. Second, post-order traversal. The children of a node are visited before the node itself. So probably it's going from bottom to top. The root is visited last. Yeah, 100% bottom to top. Every node is visited after its descendant. So you already know what descendant and ancestors means, right? Not have to worry about that. Algorithm. Traverse the left subtree in post order. Post order means bottom to top. And then traverse the right subtree in post order. Then visit the root node. Each node is traversed only once. The time complexity of post order traversal is T, and same thing where n is the number of nodes. So Maya, can you just verify this content also? Maybe just verify wherever you feel that it probably needs more content or probably needs more organization, because these are all exam related questions. So we should ensure we have good enough content for them.
Yeah,
Uh,
this looks good.
okay.
We might have
If
to
they are,
put the example also.
okay, if they are from book, brilliant. But yeah, just look at them once. Binary tree traversal, in order traversal, the left subtree is visited, then the node and the right subtree is visited. Okay. Traverse the left subtree, but in which order? Post order or pre order? That's not telling us. Visit the root node. I think it's going from the bottom then. Going from here, going to the root node, then
Yes.
traversing that. Okay. Pre order. Oh, nice. This is pretty good. It's pretty good. Pre order 1, 12, 5, 6, and then 9. In order, okay, let's do post order first. This is good example, Kritika. You wrote that, right?
I think this one Sumaya
I
wrote.
added it.
Okay, this is good. So that way we can get to know what's actually the order we can explain in the exam. Okay, so then post order. So pretty sure this is reverse, which is 5, 6. So first going children, then you're going to the parent, then 9, then the root. So left and then the right. If there was something here, then would have gone here after 12. In order is going from the bottom, going to the root, and then going on the right. So 5, and then 12, and then 6, and then 1, and then 9. Cool.
This does not follow that the left should be smaller and the right should be bigger, right? Because then 12 would be at the root node.
Yeah, it doesn't look like it does.
Yeah, it doesn't follow that.
But all binary trees follow that, right? No?
No, a
Mm,
binary search tree is ordered like that, I think.
Oh, okay. All right.
yeah. But binary tree, one rule is for sure that should not have more than two children.
Hmm.
I believe that
Yeah.
is. Kruskal's, we'll breeze through it. We have 5 minutes. We'll breeze through it. Kruskal's algorithm is used to find the minimum spanning tree for a connected weighted graph. The main target of the algorithm is to find the subset of edges by using which we can traverse every vertex of the graph. First, sort all the edges from low weight to high. Now take the edge with the lowest weight and add it to the spanning tree. If the edge to be added creates a cycle, then reject the edge. Continue to the edge until we reach all the vertices and a minimum spanning tree is created. The time complexity is OE log E, V log V, where E is number of edges. Application, layout, electrical wiring among cities, LAN connection. Okay, so I put an example video also, which you guys can watch later on. Let's take an example here. Suppose a weighted graph is this. So this is our graph. The weight of the edges of the above graph is given below. So AB, which is this, as 1, AC, which is this line as 7, AD is 10, and so on and so forth. Now, the edges, uh, why are they different? AC, DE. Why is there repetition? Okay, let's start constructing the minimum spanning tree. First, add the edge AB with weight 1 to the MST. Oh, I know what this is doing. So they reorganized it in order. So what they're doing? From lowest to highest. So what they did was they first placed all of these lines which are connected with the nodes information. Like AB, they put 1. For BC, they put 3. For CD, they put 4. So on and so forth. Then they reorganized the same data cells into this order from the lowest to highest, and then they picked up from here. So now they're going to start drawing A, B, D, E, B, C, and so on and so forth. And the shape of that will be following this. So if they encountered AB, they're using this direction. Whatever is there, they're kind of replicating it, but only picking up the ones which is in this edge and weight table. Now it's DE, so they should be picking up this shape. So after this comes this. So DE in this shape. So there you go, D. Okay, so similarly to do all the shape, but you have to ensure you're not supposed to complete the cycle. Like you can't do AC here because that will complete the cycle, that will kind of lock it. So whatever you're drawing, you have to make sure you don't complete the cycle. So you go on with that. You draw that again. This is not completing cycle because this edge is open. So one of the edges needs to be open. And finally we reach here. So we add those sums, we get 10. So total number of edges above the tree equals the number of vertices minus 1. So it's always like minus 1, whatever that number is. So the algorithm stops here. So then this is just an explanation of what they have done on the top. If you watch this video, I think this is from the Gate Smasher, and the one I put it there, you'll get also a better understanding. But it's the same thing that I've just explained to you. Cool. So I think I finished in time efficiently, 1 minute before. Uh, so that's good, and I can sleep peacefully now because we studied good enough today. So let's meet
Yeah.
between 5 to 7 session, and then we'll try to keep it early. Maybe I'll try maybe 8:30 something. I know as it progresses towards the night, we kind of go dead. Our mind stops working. At least mine stops working. I have to focus really hard today to remember things. So I'll try to keep it as early as possible. But yeah, we definitely need a gap between the two sessions.
Yeah, maybe we should do data structures first.
Data structures.
We should do
Uh,
that first because it's
oh,
harder.
yeah, you're
Yes.
right. You're
Hmm.
right. Yeah, let's do that. So tomorrow we'll reverse that. I don't know if Kritika will be available at 5 or not.
I will be available every day, all times now till the exam.
Awesome. Just 3 more days, yeah?
Yes.
Okay, awesome. So without taking any more time, don't want to cross that 15 mark. See you guys. Good night. See you tomorrow.
Yes. See